1. Defining and evaluating a logarithmic function. Essential question. What is the inverse of an exponential function f of x equals b of x, where b is greater than 0 and b is not equal to 1? And what is the value of the inverse of f of b to the n power for any real number m? The inverse of f of x equals b to the x is, and we'll say that the inverse of f of x equals log base b to the x power, or to the x. Understanding logarithmic functions as inverses. An exponential function such as f of x equals 2 to the x accepts values of the exponent as inputs and delivers the corresponding power of 2 as outputs. The inverse of an exponential function is called a logarithmic function. For f of x equals 2 to the x power, the inverse function is written the inverse of f of x equals log base 2x, which is read either as the logarithm with base 2 of x or simply as log base 2 of x. It accepts powers of 2 as inputs and delivers the corresponding exponents as outputs. Graph f of x equals the inverse of f of x equals log base 2x using the graph of f of x equals 2 to the x shown. Begin by reflecting the labeled points on the graph of f of x as on the graph of f of x equals 2 to the x across the line y equals x and labeling the reflected points with their coordinates. Then draw a smooth curve through the reflected points. All right, let's do that. So we've got negative 2, 0.25. So that's going to be 1/4 negative 2. So about right there. Okay, so let's see, that's going to be 0.25 negative 2. And then next we have negative 1, 0.5. So that's going to be 0.5 negative 1. All right, so we got, let me write that a little bit further down. That's going to be 0.25 negative 2. And that's going to be 0.5 negative 1. And then you have 0, 1. Well, that's going to become 1, 0. So that's 1, 0. And then you have 1, 2. That's going to become 2, 1. So 2, 1 is right there. And then 2, 4 is going to become, let's see, 2, 1. That's 2, 4 is going to become 4, 2. So 4, 1, 2 right there. And in 3, 8 is going to become 8, 3. So 8, 1, 2, that's going to be right there. So my handwriting is a little bit too big for some of these. All right, it's going to look something like this right here. Missed that one. And it looks something like that right there. It gets closer and closer there. All right. So that's what that looks like. Using the label points on the graph of the inverse of f of x, complete the following statements. So those points that we had, the inverse of f of 0.25 equals log base 2 0.25, and that equals negative 2. F of or the inverse of f of 0.5 equals log base 2, 0.5, 0.5, and that's negative 1. And the inverse of f of 1 equals log base 2, 1, and that equals 0. The inverse of f of 2 equals log base 2, 2, and that equals 1. The inverse of f of 4 equals log base 2, 4, which is 2. The inverse of f of 8 equals log base 2, 8, equals 3. And that's because 2 to the third equals 8, 2 squared equals 4, 2 to the first power equals 2, 2 to the 0 power equals 1, and so on. All right, reflect. Explain why the domain of f of x equals 2 to the x doesn't need to be restricted in order for its inverse to be a function. The exponential function f of x equals 2x is a one-to-one function, so its inverse is also a function. And so let's see here. Because this here is 1, 2, 1, 1, or is a one-to-one function, so it's inverse. So its inverse is a function. All right, state the domain and range of the inverse of f of x equals log base 2x using set notation. So the domain is going to be x such that x is greater than 0. And let's go back and look at that graph for a second. See how it started here, it gets close to it, but it never actually touches it, and then it goes away from it. So x is going to be greater than 0. What about the range? The range, and again, let's go back and look at it. The range is the y value. See how that arrow goes down? So it goes way down here, and it gets closer and closer to 0, but it doesn't ever touch. But it goes down to negative infinity on the y. And up here, it's got a little bit of an angle, so it gets way out here. So it will reach infinity on x, but it also reach infinity on y. So we're going to say the range is going to be y such that negative infinity is less than y, which is less than positive infinity. Identify any X-intercepts and asymptotes for the graph of the inverse of f of x equals log base 2x. So we're looking for intercepts. Okay, it never touches the y-axis. It gets close to it, but it never touches it. It crosses the x-axis here at 1, and then it keeps on going up out this way here. Okay, so there are no horizontal asymptotes. And the y-axis may serve as a vertical axis or vertical asymptote. So let's see here. The graph has an x-intercept at x equals 1 and no y-intercept. Okay, it has no horizontal asymptote, but the y-axis and that's x equals 0. The y-axis is the graph's vertical asymptote. If the inverse of f of x equals log base 2x, is that an increasing function or a decreasing function? It is an increasing function. An increasing function. You read it from left to right. What is it doing from left to right? It's going up like this. Okay, so that's increasing. It's getting larger and larger. And let's see. Does the inverse of f of x equals log base 2x behave? How does it behave as x increases without bound, as x decreases towards 0? So as x approaches positive infinity, the inverse of f of x approaches positive infinity. All right. As x approaches 0, and you might say it from the positive side, the inverse of f of x approaches negative infinity. Based on the inverse relationship between f of x equals 2 to the x power and the inverse of f of x equals log base 2x, complete this statement. The inverse of f of 16 equals log base 2 16 equals 4, because f of 4 equals 16. Converting between exponential and logarithmic forms of equations. In general, the exponential function f of x equals b of x, where b is greater than 0 and b is not equal to 1, has the logarithmic function, the inverse of f of x equals log base b to the x as its inverse. For instance, if f of x equals 3 to the x, then the inverse of f of x equals log base 3 to the x. And if f of x equals 1/4 to the x power, then the inverse of f of x equals log base 1/4 to the x. The inverse relationship between exponential functions and logarithmic functions also means that you can write any exponential equation as a logarithmic equation and any logarithmic equation as an exponential equation. So take a look at the relationship. Exponential equation, b to the x equals a. Logarithmic equation, log base b, a equals x, where b is greater than 0 and b is not equal to 1. That's real handy when solving these equations. Complete the table by writing each given equation in its alternative form. Okay. Think of each equation involving an exponential Think of each equation as involving an exponential function or a logarithmic function. Identify the function's base, input, and output. For the inverse function, use the same base but switch the input and output. Think of the equation 4 to the third equals 64 as involving an exponential function with a base 4. The input is 3 and the output is 64. So the inverse function, a logarithmic function, also has a base 4, but its input is 64 and its output is 3. Think of the equation log base 5 1/25 equals -2 as involving a logarithmic function with a base 5. The input is 1/25 and the output is -2. So the inverse function, an exponential function, also has a base 5, but its input is -2 and its output is 1/25. Think of the equation 2/3 to the p power equals q as involving an exponential function with a base of 2/3. The input is p and the output is q. So the inverse function, a logarithmic function, also has a base of 2/3, but its output is q, and its input is q and its output is p. Think of the equation log base 1/2 m equals n as involving a logarithmic function with a base of 1/2. The input is m and the output is n. So the inverse function, an exponential function, also has a base of 1/2, but its input is n and its output is m. All right, and that's what we just talked about. So B, exponential function, 3 to the 5th equals 243. So we're going to reverse it. Log base 3, 243 equals 5. Now here we have log base 4, 1/64 equals -3. So now we're going to have an exponential function 4 to the -3 power equals 1/64. Now we have an exponential function 3/4 to the r power equals 5 or equals s. So we're going to have log base 3/4 s equals r. Here we have log base 1/5 v equals w. So 1/5 to the w power equals v. And that's basically what I just did here. Think of the equation 3 to the 5th equals 243 as involving an exponential function with a base 3. The input is 5 and the output is 243. So the inverse function input is 243 and its output is 5. Think of the equation, a bit too high. Think of the equation log base 4, 1/64 equals 3 as involving a logarithmic function with a base of 4. The input is 1/64 and the output is -3. So the inverse function, an exponential function, also has a base of 4, but its input is -3 and its output is 1/64. Think of the equation 3/4 to the r equals s as involving exponential function with a base of 3/4. Its input is r and its output is s. So the inverse function, a logarithmic function, also has a base of 3/4, but its input is s and its output is r. Think of the equation log base 1/5 v equals w as involving a logarithmic function with a base of 1/5 and its input is v and its output is w. So the inverse function, an exponential function, also has a base of 1/5, but its input is w and its output is b. A student wrote the logarithmic form of the exponential equation 5 to the 0 power equals 1 as log base 5, 0 equals 1. What did the student do wrong? What did the student? Well, the student forgot to switch. The student forgot to switch the output and the input. So when writing the logarithmic equation, so the correct one would be log base 5, 1 equals 0. That would have been correct. Our turn. Good deal. Now we get to do one ourselves. So here we have 10 to the 4th power equals 10,000. So we're going to have log base 10, and now we're going to switch the output and the input. So we'll put 10,000 equals 4. Again, we're going to have log base 2. So we're going to have our base is going to be 2, but instead of 1/16, we're going to have negative 4, and that will equal 1/16. 2 to the 5th to the c power equals d. So now we're going to have log, that's a terrible looking d, log to the 2/5 power, and see, we're going to put the d here and the c there. We're going to swap the d and the c. So here we're going to have 1/3 and to the y power equals x. Okay, so we just switch those each time. Not a problem. Explain 2. Evaluating logarithmic functions by thinking in terms of exponents. The logarithmic function f of x equals log base b x accepts a power of b as an input and delivers an exponent as an output. In cases where the input of a logarithmic function is a recognizable power of b, you should be able to determine the function's output. You may find it helpful first to write a logarithmic equation by letting the output equal y, and then to rewrite the equation in exponential form. Once the bases on each side of the exponential equation are equal, you can equate their exponents to find y. So go ahead and look through example A, and when you get back, we'll do example B together. All right, glad you're back. So f of 4 equals y. So log base 1/2 4 equals y. We're going to rewrite that as an exponential function. 1/2 to the y power equals 4. Well, you know 4 is 2 squared, right? So we'll have 1/2 to the y power equals 2 squared. Well, we can make this 2 into a 1/2 by putting a negative in front of that. So 1/2 to the y power equals 1/2 to the negative 2 power. So y equals negative 2. So f of 4 equals negative 2. All right. Now, let's just for giggles, let's try that in a calculator. So we have open parentheses, 1, control, divide, 2. And let's close the parentheses. Close the parentheses. And then caret negative 2. That should give us 4, right? Ah, it does. Well, that worked out well. F to the 1/32 equals y. So the log base 1/2 to the 1/32 equals y. 1/2 to the y, we're writing it as an rewrite as exponential. 1/2 to the y equals 1 over 32. Well, we know 32 is 2 to the 5th power. 2 to the 5th power. So 1/2 to the y power equals 1/2. And then we can move this up by putting a negative in front of it. So 1/2 to the negative 5. I'm sorry. 1/2 to the 5th power. So y equals 5. So f of 1 over 32 equals 5. And let's try that. Let's try that. Almost messed it up there. Let's just go up there and we'll grab that. And then we'll change the 2 to a 5. So 1/2. And that should give us 1 over 32. And it did. Good deal. All right. F of 2 times the square root of 2 equals y. So log base 1/2, 2 times the square root of 2 equals y. So 1/2 to the y power equals 2 to the square root of 2 times the square root of 2. Okay? All right. So now we have 1/2 y equals, or 1/2 to the y power equals the square root of 2 times, because the square root of 2 squared is 2, right? All right. So that's going to give us the square root of 2 to the 3rd power, right? And now this is kind of tricky. This is a square root, right? So we put a 2 right there. We put a 2 right there. We can rewrite this as a fraction as 3 over 2. So 1/2 to the y power equals 2 to the 3/2 power. And to change this 2 to a fraction, we'll make this negative 2/3, right? So y equals negative 2/3. So f of 2 times the square root of 2 equals negative 2/3. Cool. We did it. Our turn. All right. If f of x equals log base 7x, find 243. Okay. What do we need to do first? What do we need to do first? Let's rewrite it as let's see here. Might want to first write it. So we're going to have log base 7, 343 equals y. Now, let's rewrite it as 7 to the y equals 343. We rewrote it there in the exponential form. That almost looks like something else. All right, so 7 to the y equals 343. Well, 7 to the y, all right, and 343, that happens to be 7 to the 3rd power. Okay, so y equals 3. We got rid of the bases there, and y equals 3. So f of 343 equals 3. Now, let's see. Log base 7, 1 over 49 equals y. All right, good. So we have 7 to the y power equals 1 over 49. Okay. 7 to the y power equals, that's 1 over 7 squared, right? 7 squared is 49. 7y equals, now this isn't, we can move that on the other side of it by making that a negative, right? Now we can get rid of the bases, and we got y equals -2. So f of 1 over 49 equals -2. And the square root of 7. So we're going to have log base 7, the square root of 7 equals y. Let's rewrite it as an exponent. 7y equals the square root of 7. 7y equals, well, this is 7 to the 1/2 power, right? So y equals 1/2. So f of the square root of 7 equals 1/2. Good. Evaluating logarithmic functions using a scientific calculator. You can use a scientific calculator to find the logarithm of any positive number x when the logarithm's base is either 10 or e. When the base is 10, you are finding what is called the common logarithm of x, and use the calculator's log key, because log base 10x is also written as log x, where the base is understood to be 10. When the base is e, you are finding what's called the natural logarithm of x, and use the calculator's natural log key, because log base e to the x is also written as the natural log of x. All right, so you go ahead and do A, and then when you get back, we'll do B. 0.42. First, find the common logarithm of 0.42. Round your result to the nearest place and raise 10 to that number. I'm going to go ahead and use the inspire. So let me get that. So we're going to press the log key, log, and then we're going to leave that blank, and I'll show you. And then we're going to put 0.42, press equal, and that gives you -0.3767. So we got -0.377. All right, now we're going to put -0.377 in here. So we'll try that. 10 caret -0.377. And that'll be approximately 0.42, real close, right? And it's off just because of rounding error. All right, next, find the natural logarithm of 0.42. So the natural logarithm of 0.42, so natural logarithm, that's going to be control and then e to the x. Natural logarithm of 0.42. Enter. That's -0.8675. So we'll put 0.868. 0.868. Negative 0.868. Now let's put e to the -0.868 and see what we get. E to the -0.868, and it should be real close to it is. See, it's off just by a little bit. And that's, again, we had to round a little bit here. So let's see here. So e to the -0.868 is approximately 0.42. For any x is greater than 1, y is log base x less than the natural log of x. Why is that? Well, let's see. Log x has a base of 10, right? Has a base of 10. And natural log of x has a base of e. I didn't draw e. Well, what is e? E is 2.71 and so on, right? Well, so 10 is greater than e. So the number to which 10 is raised to obtain x should be less than the number to which e is raised to obtain x. Okay, did we not notice that on the calculator? Look, 10, that's 0.41975. That's 0.41979. Okay, not by much, but it is a little bit. Because 10 is greater than e, the number to which 10 is raised would be less than the number to which e is raised. And that, see, look, see, that's negative 0.377. That's negative point. You get what I'm saying. All right. Use a scientific calculator to find common logarithms and natural logarithms of the given number. All right, so let's do that. Verify each by evaluating the appropriate. So we're going to do log 0.25 and see what that is. Log 0.25. Let's see. Control tab 0.25. And that's going to give you approximately negative 0.602. Negative 0.602. So now we're going to do 10, and let's just go, we're going to go up and grab that whole thing right there. See what that gives us. See, but if we had just done 10 to the negative 0.602, it would have been approximately, see, off a little bit. All right, so 10 to the negative 0.602 is approximately 0.25. Now let's do the natural log. Natural log of 0.25 is that. Now if we do this, and again, if we go up there and grab that, it's going to be, right. Okay, that was right on. Okay, that worked out real well. So the natural log of 0.25 was approximately negative 1.386. So e to the negative 1.386 is approximately 0.25. Now what about 4? Okay, natural log of 4, or excuse me, the log of 4 is 0.602. So the log of 4 is approximately 0.602. So 10 to the 0.602, and let's try that. 10 to the 0.602, it's going to be approximately, see, that's pretty darn close. But if we had done this, and like I said, if we'd gone up and grabbed that, it would be right on the money, right? Okay. But you want to type all them in? I don't want to type all those in. All right. So that's going to be approximately 4. The natural log of 4, is 1.386. 1.386. Back to log of 4, that's approximately 1.386. So e to the 1.386 is going to be approximately 4. And e to the 1.386. And see, it's almost 4. Okay. Now, do you notice that this is, what is 0.25? That is 1/4, right? Look, negative 0.6 and positive. Negative 1.386, positive 1.386. That's kind of interesting. Explain 4. Evaluating a logarithmic model. There are standard scientific formulas that involve logarithms, such as the formulas for the acidity level, pH, of a liquid and the intensity level of sound. It's also possible to develop your own models involving logarithms by finding the inverses of exponential growth and decay models. So go ahead and read through 4. And you might use this in chemistry. Hint, hint. All right. This bacteria here is used to turn milk into yogurt. The population P of a colony of 3,500 bacteria at time t in minutes can be modeled by the function P of t equals 3,500 times 2 to the t over 73 power. How long does it take the population to reach 1,792,000? All right, solve P equals 3,500 for t. Okay, so we got P equals 3,500 times 2 to the t over 73 power. So first off, we want to divide everything by 3,500, right? So we'll have P over 3,500 equals 2 to the t over 73. Now, we need to rewrite this in log form so that we can get rid of that 2. So log base 2 times P over 3,500 equals, and then, and if you'll watch, log base 2, that equals 1. So that's how that gets rid of that. Let's try that in the calculator. Log base 2, that gives you 1. So that cancels out. It's kind of like dividing by something. You know what I'm saying? All right. So that gives you t over 73. So now we're going to multiply both sides by 73. And we get 73 times log base 2, P over 3,500 equals t. Now use the logarithmic model to find t where P equals 1,792,000. So if t equals 73 log base 2 P over 3,500 equals 73. So we're going to put the 1,792,000 in for the P. All right. And then 1,792,000 divided by 3,500. I think that's about 512. Okay. And so 73 times log base 2, 512 equals 73 times, well, log base 2, 512 is 9. So 73 times 9 is 657. So the bacteria population will reach 1,792,000 in 657 minutes. And if you divide that by 60, that's about 11 hours. Okay. Cool. Our turn. The intensity level L in decibels of a sound is given by the formula L equals 10 times log base I over I sub 0, where I is the intensity in watts per square meter. W divided by M squared of the sound, and I sub 0 is the intensity of the softest audible sound, which is about 10 to the negative 12 watts divided by W divided by M squared. What is the intensity of a rock concert if the sound has an intensity of 3.2? Okay. So what do we got here? We've got L equals 10 log, and then I, that's going to be 3.2 divided by 10 to the negative 12. Okay. And so let's rewrite the L equals 10 log, and that's going to be 3.2 times 10 to the 12th power. Okay. So log 3.2 times 10 to the 12th power, that's going to give you 10 times, and that's about 12.5, which is 125. 125. So the sound of the rock concert, so the sound of the rock concert has an intensity level of about 125 decibels. Isn't that cool? The mass in milligrams of beryllium-11, a radioactive isotope, in a 500 milligram sample at time t in seconds is given by the function m of t equals 500 e to the negative 0.05 t. When will there be 90 milligrams of beryllium 11 remaining? So let's see here. M equals 500 E negative 0.05 T. Okay. Let's see. So we're wanting to know what T is, right? So we need to solve for T here. Okay. So let's divide everything by 500, and that's going to give us m over 500 equals e to the negative 0.05 t. So we're going to multiply both sides by the natural log. So that will cancel that out, and we have the natural log of m over 500 equals negative 0.05 t. Now, we're going to divide both sides by negative 0.05, and at menu to fraction, let's convert that to a fraction. That's 1 over 20. So let's multiply both sides by 20, negative 20. So negative 20. And that's going to give us negative 20 natural log of m over 500 equals t. Good. Now, let's put, find t when m equals 90 milligrams. All right. So t equals negative 20 natural log, and we'll put 90 over 500. Okay. And let's see. So that's going to be negative 20. natural log of 90 over 50 is, well, that's the natural log of 0.18, and negative 20. Natural log of 0.18 is going to be negative 1.715, I think. And then you multiply those together, and you're going to get about 34. That's going to be approximately 34. So there will be 90 milligrams of beryllium 11 left after about 34 seconds. Cool. What is a logarithmic function? Give an example. Well, let's see. Logarithmic function is a function with a given base that accepts a power of the base as an input and outputs the exponent for the base. And let's see here. Let's see. A function with a given base that accepts a power of the base as an input and outputs the exponent for that base. All right. So if you had, let's see, log base 2 64 would equal 6. So 2 to the 6 equals 64. And let's try that. 2 caret 6, that's 64. And then so log base 2, 64, and that should give us 6. It does. Good. That worked out. How can you turn an exponential model that gives y as a function of x into a logarithmic model that gives x as a function of y? Okay, so solve for x in terms of y. Solve for x in terms of y. Basically 3 steps. All right, first step, isolate the power of the base on one side. Two, rewrite the equation in logarithmic form. And then 3, isolate x. Not too shabby. Number 17, write the inverse of the exponential function f of x equals b to to the x power, where b is greater than 0 and b is not equal to 1. So the inverse of f of x equals log base b x. Not too shabby. All right, folks, have a good evening, and I'll see you tomorrow in class.